Validation looks at whether the mathematical model we solved is an accurate representation of the physics of the problem. And for that, we need to compare with experimental data. We already compared the pressure coefficient from experiment with our results, and we got excellent comparison there. And we also have, lift and drag coefficients to compare to. And for the lift, we did monitor the lift and drag coefficients as we were iterating. We can also calculate it under Rapport's forces. So let me do that. And first, let's take a look at the lift. The direction of the lift is, so I need the x component. This is the same as what we entered before. Okay, that's negative because the lift is tilted back with respect to the y-axis. Okay, and I say print. And since my reference values are set, I can take a look at the lift coefficient. So the total lift coefficient is around 1.06, which is very close to here. In fact, this angle of attack is slightly higher. So that's fairly, that's very close, the lift coefficient. And you can see, and so this gives you, the lift coefficient is calculated by integrating the pressure and the viscous shear, as I talked about before. And the viscous shear doesn't contribute, really anything to the lift, and it's coming from the pressure difference. What about the drag? So we have a good prediction for the lift, and I can go and do the same thing for the drag. So I need to change the direction. So that's cosine alpha, and that's sine alpha. So I need to get rid of the negative sign. And I say print. And so the total drag coefficient is around 0.017 as opposed to 0.012. And, so that's like over 40%, around 40% error. That's too high, but you can see that the lift coefficient is like, 1% of the drag coefficient is 1% of the lift coefficient. So it's much more challenging to compute. And you can see that you're getting contributions from both the pressure and the viscous shear. In fact, I was surprised that the contribution from the pressure is higher. I was expecting most of the contribution to come from the viscous shear, and that might be because of the thickening of the turbulent boundary layer near the trailing edge. And in fact, we might be over predicting that. And the way to fix that is to refine the near wall mesh and resolve the viscous sublayer and go to enhanced wall treatment. But we have a pretty good mathematical model, and I think once we get a good near wall mesh, the K epsilon turbulence model and Reynolds, the Reynolds averaging and the K epsilon turbulence model is a good enough mathematical model for this particular case.